Hi students, welcome to my lectures. My name is Dr. Surendra. I would like to say thank you to my all viewers and my students for understanding my effort in delivering the lecture. I have delivered previously the chemical reaction engineering part 1, where we have discussed about various reactors. And I am going to start a new lecture series, that is Chemical Reaction Engineering 2. In this, the main important topic that comes at the beginning is called analysis of non-ideal reactors. Means in CRE1 we have discussed about the ideal reactors. That means there is a definite formula that you have to apply to find out volumes and conversions. But when it comes to the non-ideal reactors, which is the case in the industries, then how to predict the conversions? Because when I talk about the ideal reactors, the reactant molecules are not going to spend same amount of time. That means not every molecule that enters the reactor spends same amount of time in the reactor for a given product. So, if that is the case, then we have to identify somehow if the reactor is behaving non-ideally, then somehow we have to quantify that non-ideality and predict the conversions for a given volume, or for a given volume of the reactor, and what is the conversion. So, there is a particular set of analysis existing still to find out the problems in the reactors, that is non-ideal reactors. The most popular method of identifying the non-ideality in the reactors is the tracer curve experiments. That means you somehow find out how the molecules are spending in the reactor. And the way to find out is through to detect the non-ideality, people use the tracer. Tracer is such a molecule which mixes with the regular reactants, where we can able to find the time spent by the molecules. That means if you put it some kind of tracer which can be detected at the exit of the reactor. So, based on the detection of how many molecules or tracer are coming out of the reactor at different times, if we can able to detect some time information of the molecules through which we can able to connect or figure out the non-ideality in the reactor. So, once you can able to find out the non-ideality of the reactor, that means if the reactor is behaving non-ideally, we have to somehow change the configuration or design of the reactor based on the kind of non-ideality it is facing. So, let us move ahead, and for the beginning of the particular series, that means non-ideal reactors. So, for this you need to have some background of CRE1, which is Chemical Reaction Engineering 1 concept. So, before you jump into the jump into the non-ideal reactor concept, you should cover the previous series, that is Chemical Reaction Engineering 1, where we have discussed about PFR, that means plug flow reactor, a CSTR, packed bed reactor. So, you need to have small idea what this ideal reactors are. So, based on the information that you going to gather what ideal reactors are, so we can able to find out what is the non-ideality. So, this ideal reactors is behaving like a non-ideal reactor. So, I request you people to go through that. Okay. So, in the present lecture series, I am going to start with the non-ideality and what exactly non-ideality is, how to quantify this non-ideality, and what are the tracer curve experiments, how many kinds of non-ideality we can able to find out. This sort of information we can able to get from this particular lecture series to start with. Later on I am going to add some heterogeneous reactions kind of. So, and that's a later part of the CRE2. So, let us start the most interesting topic, of non-ideality in the reactors. Thank you. Let us continue the lecture, as the lecture series starts with the non-ideal reactors. That means I represent the non-ideal reactor with a circle, right? The circle takes even CSTR or PFR or packed bed reactor, any reactor which is behaving non-ideally, we can represent with a circle where inlet the reactants are coming in, products are going out. So this is the representation we follow. Let us move ahead. So the concept of non-ideal reactors. Okay, if this is a non-ideal reactor which is having the volume of V. In this non-ideal reactor, conversion we are expecting is X, right? And this non-ideal reactor could be CSTR, could be PFR, or it could be PFR or any other reactor. So the difference between non-ideality and ideal reactor is the ideal reactor follows certain design equations. For example, the CSTR follow V is equal to FA0 into X by minus RA. FA0 is a molar flow rate. X is the conversion in this particular reactor. RA is the rate of reaction. PFR, the plug flow reactor, follows the design equation. Volume of this particular plug flow reactor is integral 0 to X FA0 by minus RA into dx. And when it is the case of packed bed reactor, the weight of the catalyst required for a specific conversion X in this reactor is 0 to X FA0 by minus RA dash into X. So RA dash is representing the rate of reaction with respect to mass. Okay, don't worry. That means the ideal reactors follow certain equations, whereas non-ideal reactor, which could be CSTR could be non-ideal, PFR could be non-ideal, packed bed reactor could be non-ideal, any reactor which is behaving ideally, non-ideally, is representing with a circle, right? So the idea of this concept of non-ideal reactors, find out the conversion. If CSTR is behaving non-ideally, what is the conversion of the CSTR? If PFR is behaving non-ideally, what is the conversion of this particular non-ideal PFR? If packed bed reactor is behaving non-ideally, what is the conversion that we can expect from this non-ideal packed bed reactor? This is the whole concept of non-ideal reactors. So that is why it is represented. Non-ideal reactor can be PFR, packed bed reactor, CSTR. Okay, to predict the conversion for a given volume or volume for a given conversion, we need to find out two different aspects of non-ideal reactors. One is residence time of the molecules, and second is what is the kind of level of mixing happening in this non-ideal reactor. If we can able to find out these two informations, we can able to find out the conversion. The objective is to estimate the conversion in this non-ideal reactor. So initial part of our discussion, concentration of this particular residence time. What is the resistance? What is the average time spent by the molecules which are entering into the reactor? That means not every molecule spends the same amount of time in the reactor. Few molecules exits after 5 minutes. Few molecules may exit after 10 minutes. Few molecules exit after 30 minutes. So depending upon the time that is spent by the molecules, the information of time we can able to get from the residence time distribution. Okay. So not just a time information is enough to find out the conversion. We need to find out how molecules are mixing with each other in this particular reactor. That is also required to find out the particular conversion in this non-ideal reactor. So entire discussion of non-ideal reactor is to find out the time information and find out the mixing information. When you have these both information, you can able to find out the conversion in a reactor for a particular order of reaction. Okay, because ideal models will not predict the conversion. That means these are the ideal models. This equation will give the information about the volume of the CSTR for a given conversion. This information, volume of the PFR for a given conversion. The mass of the catalyst for a given conversion in the reactor. These are the ideal laws. So non-ideal reactor will not follow this particular ideal laws. So let us move ahead and further into the concept. Okay, the concept of non-ideal reactors designed in a schematic representation in this particular way. Imagine there is a non-ideal reactor which could be CSTR or PFR or packed bed reactor. Let us divide the molecules in this particular non-ideal reactors into number of fractions. Okay, fraction 1 consisting of the molecules of age 1, fraction 2 consisting of molecules of age 2, fraction 3 consisting of molecules of age 3, fraction 4 consisting of molecules of age 4. What is this age representing? Example, this particular box is one particular fraction. This fraction of molecules which is spending the time between 0 to T1 is given as 1. Okay, that means this particular box, that is this particular fraction of molecules, spend the time between 0 to T. This particular fraction of molecules, set of molecules, spend the time between T1 and T2. This particular fraction of molecules spend time between T3 and T4, and this particular fraction spent by the molecules between the time T4 and T5. That means you can imagine all the molecules in this particular non-ideal reactor divided into number of fractions, and every fraction has specific time. Okay. So how to detect? Imagine the conversion, that means if, for example, if every molecules, that is every set of molecules is spending different amount of time in the reactor, the conversion from this complete non-ideal reactor comes from different fractions. That means there is some average conversion in this particular reactor which comes from the different set of molecules. So if somehow we can able to identify what fraction of molecules spending in the time, so we can able to get the conversion of this particular age plus average of all the different ages inside the molecule, we get average conversion in this particular non-ideal reactor. So entire objective of this particular non-ideal reactors is to find out the time of different fractions spending the molecules. And second thing is mixing. Imagine I know this particular age 1 molecules spend time in the reactor between 0 to T1, but between this 0 to time T1, this particular age molecules interact with the age 2, age 3 and age 4. If it starts interacting with, you can see the arrows. Okay, I have represented the interactions through arrows. That means age 1 molecule can interact with age 2, age 3 and age 4. Similarly, age 2 molecules can interact with age 1, age 3, age 4. That means before it exits between the time 0 to T1 from the reactor, it is going to interact with different other fractions. That means if it starts interacting, the conversions will be different. If this particular fraction will not interact with any of the other age molecules, the conversion from this reactor age can be estimated using a batch. Okay, that means this particular batch reactor spend time 0 to T1. So the conversion from this age 1 can be estimated, assuming that this is a batch reactor. So the conversion from this batch reactor is between the time 0 to T1. So conversion from this particular batch reactor, which is of age 2, can be estimated from the batch reactor equation. So between the time T1 and T2. Similarly, different fraction of molecules can be segregated in terms of batches. So every batch spending different amount of time have different amount of conversions. Not just a batch reactors. Imagine if this particular batch of molecules interacting with age 2 and age 3 and age 4, that means the conversion will be mixed up. Okay, that means if this batch is not interacting with any other batches, the conversion will be different. If this batch is interacting with other age molecules, the conversion will be different. That means mixing is also plays an important role. That means not just a time spending inside the reactor, along with the time spent inside the reactor, how much mixing is happening among the different age molecules is also important to find out the conversion. So the simplest way to find is see the the molecules, how they mix, it is difficult to assume. Only we can able to find out what is the age of different molecules in the reactor. Okay, how to find out the age of different molecules in the reactor is through tracer injection or tracer curve experiments. Okay, how you can see the red. Okay, you can see the red circles. I represent the tracer. Okay, the blue ones is the regular reactants which is coming into the reactor and exiting the reactor, and the one which is showing as a red circle is called our tracer. Okay, to find the information about the time of different molecules in the reactor, what we do is, along with the regular molecules, inject some amount of tracer molecules. This tracer molecules will also mix along with the reactants, goes into the reactor. This tracer molecules will not react with any other molecule. It is just along with the reactants, it is also spend time in the reactor, the tracer. So if you inject certain amount of tracer through an injection, certain amount of tracer, it will mix up with the regular molecules, goes in the reactor, and it will spend certain amount of time in this particular reactor and exits along with the products or reactants. So at the end of the non-ideal reactor, which could be PF4 or CST or a PBR, a detector is placed where it can directly detect how much amount of tracer molecules is coming out. Okay, this is called tracer detector. You can able to titrate, so the tracer molecules you can able to put or HCl or NaOH. So you can able to, when the tracer molecule comes out, if it is a HCl that you have injected along with the other reactants, while it comes out, you can take a sample. Okay, by titration with against a base, you can able to find out how much amount of HCl that is exiting the reactor. So depending upon the amount, okay, with respect to time, I take out the samples from the exit. Based on the information, I can able to find how many molecules are spending less time in the reactor, how many molecules are spending more time in the reactor. So I can able to identify on an average what is happening inside the particular reactor using the tracer curve experiment. So somehow I get an idea that depending upon the measurements of the tracer at the exit, I can able to figure out what is happening in the particular non-ideal reactor. So time information. Okay, the time information we are going to get. If you plot, there is a curve which is called residence time distribution curve. So based on how much amount of tracer that is coming out with respect to time, if I plot on y-axis E of t, and with respect to x, on x-axis it is the time, on y-axis it is E of t, I get some sort of curve based on the measurements of the tracer which is at the exit. So at the, I can say between 0 to t1 time, that means this set of molecules will come out of the reactor. So I can, from the graph, I can able to find out how many of such a molecules comes between the time 0 to t1. So based on the area information, A1 is the area under the curve between the time 0 to t1. That means based on this area, I can able to find out how many of the molecules of age 1 are between the time 0 to t1. Similarly, and with respect, if more, that means more tracer exits at a later times, I can able to find out from this curve between the time t1 and t2, area under the curve is A2. That means between the time t1 and t2, age 2 molecules are exiting the reactor. How much of the age 2 we can able to find out from the area under the graph. The area A1, A2, A3, A4, A5 talks about the directly fraction. That means A1 is the fraction of molecules that exits the reactor between the time 0 to t1. A2 is the fraction of molecules that exits the reactor from t1 to t2. You can be able to correlate t1, t2 from this graph. You can see 0 to t1, age 1 molecules comes out. T1 to t2, age 2 molecule comes out. T3 to t4, age 3 molecule comes out. T4 to T5, age 4 molecules comes out. That means you can able to find out what fraction of molecules spending the different times in the particular reactor. Okay, that is why it is represented 1, 2, 3, 4 indicating different age molecules spend time in the reactor at different times. So directly this particular square, that means I have given a fraction. Okay, directly A1, A2, A3, A4, fraction of molecules spend time between 0 to T1 and so on, which can be able to estimate it through the graphical area measurements. Zero, you can see the simple zero means it's a molecule which is entering the reactor has no age because it's still yet to enter the reactor. So once the molecules enter the reactor, depending upon the time it's spent, it will be given a specific number. So through RTD experiments, we can able to find out different fractions in the particular reactor, okay, because it is important, right? Because less is the time spent in the reactor, less is the conversion in this particular fraction. More is the time spent by the molecules in the reactor, more is the conversion. So somehow we get some estimate of what is happening in the reactor through the tracer curve experiments. Okay, let us move ahead. Non-ideality, okay, non-ideal reactors. As I have already discussed, the reactor which does not behave ideally is termed as a non-ideal reactor. Which does not behave means which does not follow this ideal design equations. Okay, this is for the CSTR, this is for the PFR, this is the packed bed reactor which we have discussed. So what were the reasons in the non-ideal reactors? That means non-ideal could be anything. It could be CSTR that is behaving non-ideally, it could be PFR that is behaving non-ideally, it could be packed bed reactor that is behaving non-ideally. So what are the possible reasons that the reactor is not behaving ideally, which is called factors responsible? Stagnant zones in the reactor, bypassing, channeling, dispersions, internal flow recirculations. These are the some factors which caused this ideal CSTR to behave non-ideally, this ideal PFR become non-ideal PFR, this packed bed reactor becomes non-ideal packed bed reactor. For example, what is this bypassing? Because you can see when the reacting molecules are entering the reactor, there is a chance that few molecules exit the reactor early and few molecules and spent more amount of the time in the reactor because of this particular stirring. And there is a possibility below this stirrer, there is a dead zone where the flow will not go through the corners of this particular reactor. That means bypassing and dead zones may be the possibility that the reactors might behave non-ideally. For example, if this is a dead zone, this is a packed bed reactor. You can see in the packed bed reactor, the catalyst is packed in the reactor. And you can see there are different zones in this particular packed bed reactor where the catalyst is heavily packed, where there might be chances where the catalyst is lightly packed. And through this particular kind of packed bed reactor, if the reactant molecules are entering, there is a high chance that there are sections in the packed bed reactor that reactant flows very fast, okay, because it is lightly packed. It will pass through with the least resistance, that means least time. There are certain sections in the packed bed reactor where the reactant molecules have to pass through number of twists and turns before it exits the reactor. That means there might be some set of molecules which exits the reactor early. There are some sets of the molecules which exit the reactor very late. And there are some sections of the molecules at the corners where dead zones. Dead zones means that particular zone a molecule will not trapped, right? There is no new molecules enters in the dead zone. There are no old molecules that exits the dead zone. These are the different possibilities we can able to go through. What is axial dispersion? Okay, when the reactant molecules are entering in the reactor, because then there is a special term called dispersion or diffusion. That means once the reactors enters the any reactor, there is a possibility because of the diffusion it might go back, it might go further. Because you can see diffusion, that means the molecules of A can diffuse even backwards and forwards because of the concentration gradients. So because of the molecules move backwards and forwards, and there is a different time will comes. Example, the molecules which move a bit backward might spend a longer amount of time in the reactor. The molecule which diffuse to the further because of the diffusion process, it exits the reactor early. That means there is the possibility that because of this particular diffusion or dispersion of molecules, the time spent by the molecules in the reactor will be different. internal flow recirculations. That means that if any molecules enters any of the reactors, it might eddy zone formations. Okay, internal flow recirculations, that means there is a possibility of eddies in the reactor which will continue to rotate at the same place, where it will trap the molecules for a longer period of time. Okay, that means there is a possibility that the reactants, few of the molecules will exit early and few of the molecules which got trapped will exit at the late. So this is how the reasons for the non-ideality. Okay, let us move ahead. Then if I know what is the non-ideality now and what are the different possibilities for this non-ideality, then how we are going to move ahead? How to design non-ideal reactor? That means this is the non-ideal. I represent the reactor in terms of circle. So these are the informations required. One is to design this non-ideal reactor, that means to predict the conversion and volume from this non-ideal reactor, I need to have certain things with me. I need to get certain things with me. One is, what is kinetics? That is, what kind of reaction happening inside. That is a first order, second order, zero order. The kinetic information I require. And mechanism, that means order comes from this part to mechanism, okay, which is extensively discussed in the part 1 of the CRE. And second is residence time distribution. That means I already told you that different molecules spend different amount of time in the reactor. So that information comes from the residence time distribution. That means identifying the fraction of molecules spending time in the reactor. Third is mixing models. That means not just time information is sufficient to predict. I need to understand what kind of mixing happening. That means how the molecules are mixing in the reactor, not just the time spent in the reactor. The mixing is also important. So there is specific models that are available, because we cannot go inside the reactor and see how mixing can happen in the reactor. So instead, people come up with the different models. So there could be zero parameter models, single parameter models, or higher parameter models are available to predict the mixing in the non-ideal reactor. And the zero parameter models includes the segregation and maximum mixedness model, and single parameter model include Tangent dispersion model and Tangent series model, dispersion model. So we get the time information from the tracer curve experiments, and we take any one of the models which is assumed models. That means I assume that something is happening in the reactor, that means some kind of mixing happening in the reactor. That assumption comes from this particular models. And if I assume the segregation model, then I put the segregation model here and predict the conversion from all the three informations. I assume maximum mixedness model. That means inside this maximum mixedness is happening, I assume. So then I use this particular maximum mixedness model and using the three information like kinetics and RTD mixing models and predict the conversion. So this is how we are going to move ahead. This is RTD, time information. The mixing models, I assume certain sort of mixing in this particular reactor, and I should know what kind of order and mechanism kind of reaction that is happening. By using these three informations, I can able to predict this conversion from this particular non-ideal reactor. Then how, let us say, this is how we going to move ahead. Now we got, let us focus on residence time distribution. That is, among the three sets we have discussed just earlier. Kinetics we already know. I mean, we presume that we already know the kinetics. Second thing is to characterize and diagnostics of non-ideal reactors. That means first of all you need to identify the non-ideal reactors. Then how to identify? Once you have identified, I mean, how much non-ideality is existing, that is called characterization of non-ideal reactor. Diagnostics, that means we need to identify what kind of non-ideality existing in a particular non-ideal reactor. So to diagnose the problems in the existing reactor, that means there could be some reactor, we have to identify if it is behaving non-ideally and how to identify that particular non-ideality. Example, the dead zone, or non-ideality in the sense, this is one I am talking about, okay, a stagnant, identification of stagnant zones, bypassing, channeling, axial dispersion, internal flow recirculation. Once we identify it, and how to quantify it, okay, how much that kind of non-ideality is there. So that is called characterization. So to identify the extent of non-ideality in the reactor, we need to have certain things that will help us. The first thing is residence time distribution curve. Second is cumulative time distribution curve. Third is what is the mean residence time of molecules, what is the variance, what is the skewness. So this is how, if we can able to do the tracer curve experiment, through the tracer curve experiment we can able to find out these particular parameters. Through this particular parameters we can identify the non-ideality and extent of non-ideality in the non-ideal reactor. So part 1. And I know once part 1, that means what we are going to discuss is understand this particular characterizations of non-ideal reactors. First apply, to find out a particular reactor is behaving non-ideally, you should know how the ideal reactor characteristics are. So let us apply, and in further we are going to apply the characterization of all the parameters to the ideal reactor, so you can have some reference point. So once you got some reference point, you can compare that particular ideal reactor behavior with a non-ideal reactor behavior. So that is why in the part 1 of the story, let us understand how this E of t, F of t, Tm, skewness of ideal reactors are. So then based on this particular reference point, we apply this particular characterization to non-ideal reactors. So then you can able to analyze the non-ideal reactors. In part 1, that means initial part of the discussion, that we are going to apply this characterization to the ideal reactors. In the part 2, we are going to discuss about the predicting the conversion in the non-ideal reactors, because I have discussed that there are certain things, that means initial part of the story, that means we are discussing about the RTD. Then part 2, we are going to deal with the mixing models. So once you add all these things at a place, then you can able to find out the conversion in a non-ideal reactor. So this is how we are going to go ahead. Let us meet with the new lecture. Thank you.